Hi everyone, I just want to point out a pretty bad mistake that I make in this video where I'm talking about countable sets and uncountable sets. Um, so so what I want to be using in this proof is the fact that countable unions of countable sets are countable. And the way you can prove that countable unions of countable sets are countable is that you can just sort of weave through the elements like in a diagonal proof. And so, like in this exercise in particular, you have on one axis you have the integers n greater than or equal to 0, and then on the other you've got elements of you got roots of polynomials of degree n. So if you look at this, like this column here, what this column has is for a fixed n, this column contains the countably many roots of polynomials of degree n. And to get the algebraic numbers, we take the unions of all of these things. We take the union over all n greater than or equal to 0 of roots of polynomials of degree n. And there are countably many positive integers n, and for each of these integers there are countably many roots that you can obtain from polynomials of this degree, because there are countably many polynomials of this degree, and each polynomial can have at most finitely many roots. Okay, and so because you've got this array that this table will give you all roots of polynomials of all orders, and thus it will contain all of the algebraic numbers. And to figure out how many of them you weave through them, like I discussed. It's like a standard diagonal argument, and you can prove that they're countable that way. Now, what I state in the proof is that you think of this as being a countable product of countable sets. Where, like, I guess what I was thinking was that, like, you have each of these columns here, and then you're sort of taking the direct product of these columns, and that will end up with giving you something that you can interpret as being a set which has the same size as the number of algebraic numbers. That is not true, because a countable product of countable sets is going to be uncountable. The only time it won't be would be if, like, because when you say a countable set, that could mean a finite set, and it could also be a set with one element. So if you have a countable product of sets and each set has just one element, then obviously all sets of this form is going to just give you one element, or it's going to give you countably many elements. But if you think of, so countable products of countable sets, if you want a good example of this, just think of it this way: 0, 1, 0, 1, 0, 1, etc., etc. So you take countably many products of the finite set containing just 0 and 1. And let's see here. So these aren't even infinite sets that we're taking the product of. These are just finite sets, and in fact they have just two elements. But if we think about this, if you take any element of this form, any element or any element of this set of numbers of this form, then you can think of it as like an ordered pair of, like, let's see here, so like A1, A2, A3, etc., etc., where AI is equal to 0 or 1 for all I, then we can sort of think about this as being, we can interpret this as a decimal, so 0.A1, A2, A3, etc., etc. And so what we have now is this actually we can use, because all these AIs are 0 or 1, we can think of this as being all binary decimal expansions between the numbers 0 and 1. And so that's going to have the same size as the number of real numbers between 0 and 1, which is uncountable. And so this already gives us an uncountable set. Okay, so that's about it. All I wanted to emphasize was that anytime in this proof that I say that I talk about a countable union of countable products, no, when I say a countable product of countable sets, ignore that and replace it with countable union of countable sets, and everything else will still work out. And it will work out because countable unions of countable sets are countable, which is what I want. And on the other hand, countable products of countable sets are not countable. And that's not what I want. So sorry about the mix-up, but hopefully this explanation will clarify that exercise. Alright, so we have a complex number is algebraic if there are integers such that z is a root of a polynomial of this form, and we want to prove that the set of all algebraic numbers is countable. And there's a hint here, but we're going to ignore the hint. So anyways, let A be the set of algebraic numbers. So for each A in A, there exists a natural number, an integer n greater than or equal to 0, and here, let me write this like this. There exists n q0, well, yeah, we need this n. And q0 all the way up through qn in z such that a is a root of the polynomial q0 plus q1x plus q2x squared plus all the way up to qn x to the n. Okay, so for each n greater than or equal to 0, there are only countably many polynomials of this form. Okay, and why is that? That's because each of q0 through qn, each of these are chosen from a countable set. So you can sort of list all the elements in each of these sets, and then you can sort of do like a diagonalization type argument where you take like q0, q1, all the way up through qn. And so you've got a list of all the possible values that these elements can take. And so you first take the first one from, you take the first element from each list, and you use those to get you a polynomial. And then what you'll do is you can take like the second thing in this list and combine it with the first thing in every other list. And then you do it like this, and so on and so forth. And basically what you do is you take every possible combination of positive integers and let those correspond to which integer in the list you're going to use for q0 through qn. And in this way, you can sort of, it's sort of a diagonalization argument, except for like the typical diagonalization arguments, you've only got two things, and so you can draw it as like a matrix, or like as a grid, and you've got one thing going this way and the other thing going this way, and you sort of weave through them like so, or something like this. But here, we have Q0 through Qn, so we can't really draw this because you would need n different directions to go in. But you can still weave through them in the same way and get a list of all possible polynomials of this form. Okay, so there are only countably many polynomials of this form, and each of these polynomials has at most n distinct roots. Thus, for each n, we can obtain countably many elements of A. Because for each fixed n, there are countably many polynomials, and for each of those polynomials, there's finitely many roots, which means that there's countably many roots of this form. And so, and each of these roots, of course, is an element of A, and so, therefore, for each n, we can contain countably many elements of A, using degree n polynomials. This holds for each n greater than or equal to 0. So this holds for each n greater than or equal to 0. Yeah, I mean, I'm starting to think, like, do I want to throw in, like, extra notation here to make this more complicated? But then just saying that question out loud makes me think no. Because we're looking at, here, let me finish writing this. And so combining, all roots of this form yields a countable set. Because what are we doing? If we want to get the set of algebraic numbers, then you need to take every single n greater than or equal to 0, and for each of those n's you need to consider all polynomials of that degree and figure out all the possible roots that you can obtain from these polynomials. And for each n, you get a countable list of roots in this way. And so you get such a countable list for n equals 0, n equals 1, n equals 2, n equals 3, etc. And then if you want to combine all of these lists together, then you can weave through these again. And here you can actually, what you would do is you would have, let's see here, so you have n going across this way, and going down this way you would have the roots of polynomials of degree n. Because what you do is for each fixed n, you look at this column here, and what this column gives you is this column in this table will give you all numbers which are roots of polynomials of degree n. And you have a list of them because it's countable. That means you have a list. And then, of course, you can just weave through this the way that you weave through the other things before. And then once you do that, you end up with a list of all. You end up in this way with the list of all algebraic numbers because any algebraic number has to, by definition, arise in this way. Okay. So now, what if we prove in? Thus, the set of algebraic numbers is countable. And of course this makes sense, and we're pretty much done with the proof at this point, but we're technically not, because what have we proven? We've proven that the set of algebraic numbers is at most countable. If you want to be really specific about what the question is asking, it says to prove that there are countably many algebraic numbers. Not that there's infinite, not that there's at most countably many, but precisely countably many. So we do have to do a little more work to prove that there actually are countably many. All we know so far is that there are at most countably many, which is the hard part. So the easy part is, how do you know that there's at most countably many? To prove that there are, in fact, countably many algebraic numbers, which I'm just realizing is just as quick to write as elements of A. Algebraic numbers. Note that each sorry, I'm using n already. Each integer m is a root of the polynomial. Well, you just take x minus m, because if you plug in m, then you get 0. And so, since this holds for every integer, the integers are a subset of A. Since the set of integers is countable, A must be at least countable. Right? Because just knowing that the integers are contained in A lets us say we know that A is a bigger set than the integers. So if the integers are countable, A is at least countable. It could be bigger. We don't know just from this alone. But we already know that A is at most countable. So it's at most countable and at least countable. Hence, A is countable. So the real important thing that we've used here is that countable products of countable sets are countable. So what I mean by that is when you're counting up the number of possible polynomials of any given degree, what you're doing is you're taking, for each coefficient, you're taking the set of things that those integers can come from, i.e. the set of integers, and you're sort of taking the direct product of these sets. Because you can think of, you can sort of think of each polynomial as, you can think of a polynomial of degree n as being an ordered pair of n integers, where each coordinate corresponds to some degree whatever term. And so when you're counting the number of polynomials of degree n, what you're really doing is you're counting the number of elements that you get when you take n direct products of the integers, and this becomes a finite direct product of countable sets, and so it's countable. And then from here, of course, for each polynomial, there's finitely many roots, and so you get countably many roots for each polynomial degree n. And then when you construct the total set of algebraic numbers, what you do is you, for each n greater than or equal to 0, you're taking roots from a countable list. And that means that you're really taking a countable product of countable sets, because there's countably many integers greater than or equal to 0, and corresponding with each of these integers greater than or equal to 0, you get a countable set. And so it's a direct product of a countable set and a countable set, and you get a countable set. It's the direct product of countably many countable sets, and it gives you a countable set by the diagonal argument. So yeah, that's really all there is to it. The fact that countable products of countable sets is countable allows you to prove that the algebraic numbers are countable, and this completes the proof.